This video goes over Pascal's triangle, which ties into combinations, a way that things are expanded, and we'll see it also how it applies to the binomial theorem, expanding binomials. So the way that Pascal's triangle is built, by adding the two entries from the row above to get the next entry. So 4 and 6 is 10. Okay, and so on. We're going to fill in the next row here. 6, 15, 20, 15, 6, and 1. So in our first row, row number 1, we have one term and the sum is 1. In our second row, we've got two terms and our sum would be 2, 1 plus 1. In our third row, we have three terms, and our sum is going to be 4, 1 plus 2 plus 1, and we're going to keep going down the rows. So 4 rows, our sum is going to be 8. Fifth row, we have 5 terms and our sum is 16. Sixth row, we have 6 terms and our sum is 32. And our seventh row has 7 terms and our sum is 64. So if we're going to predict the sum of the entries in rows 8 and 9, I would assume that it would follow the same pattern as the previous rows did, and I would get 108 and then 216 just by doubling the previous value. So in order to tie it in to combinations, we can also write the entries of Pascal's triangle using combination as shown below. So this is choose notation. This here is the same here. And then these two rows here would be 1, choose 0, and then 1, choose 1. So let's fill in the next couple of rows. We would have our fourth row, 0 with entry, fourth row, first entry, fourth row, second entry, fourth row, third entry, fourth row, fourth entry, and then we'll do our next row, fifth row, all the way across, 3, 4, and 5. And then the example is asking us to write 3 rows, so we'll write one more. And hopefully you are starting to identify a pattern in between the previous rows. So looking at these two, so the number on top is going to go up by 1, okay? And then the number on the right-hand side, or the higher one, is always staying at the bottom. So we can actually use this to write equivalent expressions for choose notation. So if we have 6 choose 2 plus 6 choose 3, I know that this is going to move me down to my next row and that the highest value is going to stay the same. I can even see that up here if I were to add one more row. So I'm looking for the entry that goes right here. So I would have 7th row, choose 0, 7th row, choose 1, 7th row, choose 2, and then 7th row, choose 3, and so on. But obviously, every time you do that, you don't want to write out all those rows. Same thing here. Now we're working backwards. You don't want to have to write out all the way to the 11th row. So we can work backwards by knowing that this number must be the sum of the two terms above it in Pascal's triangle, which would be 10, 3 and 10, 4. We can summarize this in general as Pascal's identity. So n choose r is equivalent to n choose r plus 1, or n choose r plus n choose r plus 1 is going to be equal to n plus 1 choose r plus 1. The last example that we're going to do here is on a checkerboard, which works like Pascal's triangle. So we want to determine the number of paths that a checker might take to get to each allowable square on the board if it can only move diagonally forward one square at a time. So I can move to this square here in one way, or this square here in one way. From those squares, I could also move here in one way, or I could move here in 2 ways. So I could move from this square or from the square. And here I can move in one way. I'm going to keep filling in my possibilities. Now I've got 3 ways to get to this square. And same thing here, 3 ways, and still just 1 way to get here. And I can continue filling in my moves as I go down, always adding the 2 previous squares, like in Pascal's triangle. You'll notice that the coefficients are the same. Now this one is tricky right here from the 4. I've got 4 different pathways that I can move to the next one. So same thing here on the left. I've got 5 different ways I can move to this square here. These 2 I can add 2 together. Same thing here. I've got 20 different pathways. 14 different pathways. And then I'm going to add my last ones together. 20, 35, 34, and 14. And then in order to find my total number of paths, I'm just going to add these bottom squares all together, because that is going to give me the total number of paths that I can take to get to each allowable square on the board. So my total is going to be 20 plus 35 plus 34 plus 14, which is going to give me 103 possible pathways.